Okay, so this new unit is about the indefinite integral. Last unit we had the definite integral where there was numbers on our integral symbol. Now we have the indefinite, which we will get into the details of what that is. So before, you were given a function and we found the derivative. That was all second and third quarter this year. Now we're going to be given the derivative and we have to go backwards to find the original function. So we're going to pause the video here, or you pause and try. What possible functions could give you the derivative of 2, 3x squared, and 4t? Okay, so for 2, that probably came from 2x. But I could say 2x plus 5 if I wanted. That would give me a derivative of 2. For g of x, so 3x squared, if you think about the derivative rule, the exponent became the coefficient and we subtracted 1. So this probably came from x cubed. But then I can put a constant on the end, let's say minus 10. So if I take the derivative of x cubed minus 10, do I get 3x squared? Yes. All right, and then lastly for c, the 4 is the coefficient, and the exponent is now a 1. So that means it had to start at t squared, but how do I get a 4? Oh, if we put a 2 coefficient, now 2 times 2 would give me 4. So this is 2t squared, and let's say, I don't know, plus 56. So what you've noticed I did as I showed my answers is every problem I put a constant on the end. So when we're going to be going backwards to find the function, we have to account for these constants that, well, I don't know what they were. There's no way to know what a constant was. So instead of making up numbers, what we're going to do is we're going to write plus a constant, plus c. All of these would be a general plus c for the constant to hold that spot so that when I take the derivative, I get that original problem. So the rest of the page until the bottom is a bunch of definitions and fill in blanks and official vocabulary. So I have it filled in. So there's a good portion of it. You pause the video, fill in the blanks. I'm going to explain it. So we learned back in Algebra 2 that an inverse undoes the original function. So the operation of determining the derivative, determining the original function from the derivative is an inverse. And that's called finding the antiderivative. So a capital F and a lowercase f, there's a big difference, okay? So you have to know that notation of the capital versus the lowercase. So a function capital F is an antiderivative of the original function, of a function little f, if for every x in the domain, it follows that the derivative of f, or the derivative of the antiderivative, gets you back to f. So if I go up here to label these, f is an antiderivative. So this 2x plus c would be the capital F. This is the antiderivative of 2. If f, capital F of x, is the antiderivative of lower f, then capital F plus c, where c is any constant, is also the antiderivative. So this is laying out what I explained earlier with the plus c. So it's possible that if we start with 3x squared, the antiderivative could be x cubed. It could have been x cubed minus 5. It could be x cubed plus 4. It could be x cubed plus or minus any constant. So we hold that spot, in our answers with the plus c. Anti-differentiation is also called integration, and we use the integral symbol. So the integral of f of x dx is the indefinite integral because there's no numbers on the integral symbol. In our last unit, when we had the integral from a to b, like that, this is a definite integral because I'm going from a starting value to an ending value. An indefinite integral has no bounds on the integral symbol, and it's just going to give us a family of antiderivatives. Okay, you did not see these two statements in the prior when I had the page centered, so we can write them down now. This symbol got kind of cut off in your packet. If you want to update, you fix it, like I drew in the whole integral. So we read the integral of f of x dx as the antiderivative with respect to x. That this variable x is telling me what we're referencing. It's just like when we had the derivative dy dx. That was the long way of writing y prime. But we like to see the dy dx because that told us we're using the rules with x. Okay, so we're going to take these problems and turn them into the integral symbols. So here's how that works. If I do the antiderivative of 3 dx, I will get 3x here. So it's, if you think of the inverse, it undoes the equation. It's like going backwards. So for b, the integral of 2x dx would get me x squared. And then for this derivative, see how it's a t now? The integral of 9t squared dt would get me 3t cubed as the original function. So just like with derivatives, we have some rules for integration and antiderivatives. So turn to page 4. We're going to fill in the rules and then we're going to practice them at the bottom. Okay, the constant rule, that says the integral of a constant k dx will always equal kx plus c. So k is like the number 5. The integral of 5, or the antiderivative of 5, turns into 5x plus c. You can always check yourself. If you take the derivative of your answer, you should get the integrand. So if we have a coefficient on a function in an integral, we can leave the coefficient out and do the antiderivative of the function. So this is like when we had the derivative and we would carry the coefficient down to our answer. It's the same idea, that the coefficient or the constant that's multiplied in the front is, you could leave that out, do your antiderivative rule, and then combine them. For the sum and difference rule, we just have to spell out for the purpose, oops, I wrote that wrong, hang on. It's hard to talk and write at the same time. So, if we have the sum of two functions that I want the antiderivative of, I have to tell you this rule only because it does not apply for products or quotients. So we have to say, well, for sum and differences, for adding and subtracting, it does apply. If you have the antiderivative of a sum, you can individually do the antiderivative of each part and add their integrals together. So the integral of f of x plus g of x is the same thing as if I do the antiderivative of f plus the antiderivative of g. Same thing for the difference rule. If I have the antiderivative of f of x minus g of x, I'm saying I want to find this difference antiderivative. I can split that up . as individual antiderivatives subtracted. And now the main one that we are going to use all the time is this simple power rule. It's just like how we had a power rule for derivatives. This is going to tell us if you have a basic expression with the variable. So we have x to the n. I want the antiderivative of that. The rule is I can now add 1 to my exponent divided by the new exponent plus c. This is a plus sign in here. Uh-oh. I wanted to white out that line so you could see it better. There, you gotta do it like this. It's saying you take your base, add 1 to the exponent divided by the new exponent plus your constant. You always have to have that plus constant. So if you think about an antiderivative being the inverse of a derivative, for the derivative, we subtracted from the exponent and made the original exponent the coefficient. Well, now we're going to add to the exponent and make the new exponent the denominator of the expression. So this simple power rule is what we're going to use for the rest of this page, plus with the constant rule at the top. The others in between, the constant multiple, the sum and the difference, they're just formalities to tell us that yes, you're allowed to do this. Okay, so here we go for number 3. We have a constant 1/2. I want the antiderivative of 1/2. So with a constant, that turns to 1/2 x plus c. If you want to check, take the derivative of this side and you should get the integrand, the function that you're taking the antiderivative of. So here we've got 1 dx, so that becomes 1x plus c. And now, when you have negative 5 dt, this dt is telling you, hey, use the variable t, not x, like that one. So this becomes negative 5t plus c. Okay, for 6, why do these symbols keep getting cut off? Okay, for 6, we have 3x. So this 3 is like the constant multiple rule. The coefficient can just carry down into my answer. Then I take my x, the exponent is a 1. I'm going to add 1, so 1 plus 1 is 2, divided by that new exponent plus c. So let's check. If we have 3 over 2x squared, and I do the derivative, like bring that down, subtract 1, those divide. Do I get this integrand of 3x? We do, so it worked. Now, with a variable in the denominator, I can't take the antiderivative yet. I have to move the variable out of the denominator by making the exponent negative. So now I can do the power rule. Add 1 to my exponent, divided by the new exponent, plus c. It's like negative 3 plus 1 is the negative 2. This looks weird. The negative exponent can come back to the denominator. And then I'm going to fix it just slightly more. This negative in the denominator looks funny. I like it in the numerator in the front. So that's negative 1 over 2x squared plus c. Okay, for 8, we have to make the radical into an exponent. And now we have to add 1, so 1/2 plus 1. Don't do 1.5 because we divide by the new exponent. I don't want a fraction with a decimal. That just is bad math notation. So now we're dividing by a fraction, so I can multiply by the reciprocal of the denominator to make my final answer look nice. So for 9 and 10, see how we have a sum of two terms? You don't have to write this, but what the sum rule at the top is saying is I can do the antiderivative of x plus the antiderivative of 2 and then add them together. So even when we did derivatives, we did this mentally, we split it up. So if I look back at x, I say, okay, add 1 to my exponent divided by the new exponent plus, this is a constant, so it gets the new variable, plus c. So I'm just adding individually the antiderivatives. You don't need a plus c every time. 1 plus c on each problem is all that's needed. So then lastly, for 10, we've got add 1 to the exponent over the new exponent minus add 1 to the exponent over the new exponent plus, and then all plus c. So the coefficients carry to the answer, to the antiderivative answer, and I add 1 to my exponent, divide by that new exponent. All right, now it's your time to practice. Page 5 is homework. Try these 10 problems. The answers are at the bottom, and we will go over them tomorrow.